Hi folks, and welcome back to Math with Captain Rod. Making this video here to demonstrate how to set up integrals for surface areas of revolution here. So what we're going to do, we're going to look at this function y equals x squared. I always like to start with fairly simple examples. We're going to look at the region of this function here between x equals 1 and 4, so this region right here, and we're going to imagine that region revolved about the x-axis. Now, when we take this curve, and I'm going to put this in red, right along here, and we revolve it about the x-axis, what we're going to get is a geometry that's going to look something like this. This kind of, I don't know, partial horn looking thing. And what we're going to do now is talk about how to set up an integral to calculate this thing's surface area. Now, I've already got some work here on the right that's from my previous video on how to set up integrals for arc length. This is going to be relevant for this discussion, so I left it there. The surface integral, or surface area integrals, it still starts with this, the differential element for the little arc length here that's left in green. Right? Now, when we take this green element that has a length ds, I'll do this, make the whole thing green, and we revolve this about the x-axis. What we're getting is this ring here. In this picture, it's over here. And what we need to do now is write an expression for the area of this green ring. Now, this distance is dx, or I'm sorry, ds, and then if we take that and we multiply by the circumference of this ring, which is 2 pi r, we would get an expression for the area of the ring. So I would usually write something like maybe dA, because it's a differential area, right, is going to equal 2 pi r times ds. Now the 2 pi r is the circumference of this ring. It's the distance around this way, or in this picture it's the distance around here. The r is the radius here, and I'll chat about that in a second. And then the ds is this dimension right here. Right? If you're not seeing that, just imagine like cutting this ring here and laying it out straight. And it would look like this basically. And then this distance is your circumference, 2 pi r. And then this dimension here is your ds. Now the fact that there's a little bit of curvature here doesn't matter because these are differential elements, and I'll save the y on that for another video. But so basically this cross-sectional area here, or this area, is 2 pi r times ds. Now the r is the radius of curvature. That's going to depend on your picture. I put r there to make this kind of generic. In this picture right here, this is the radius of curvature, and that's equal to the function value here. That will depend on your picture. If we were doing some other type of revolution, like imagine we were maybe revolving this ds maybe about x equals 4, the ring would be going this way, and the r would be this dimension, which would be 4 minus x in that example. So again, this is kind of in general here. Now specific to our example, the radius is equal to the function value, which I'm going to go ahead and put x squared, because this would equal y. And for ds, I'm going to go ahead and write square root of 1 plus, now this is dy dx squared. Dy dx for this function is 2x, so this is going to be 4x squared dx. Okay? So this expression now gives the area of any of these little rings, or in this picture, anywhere along here as a function of x. Now again, that's a dA, that's a differential a because they're infinitely thin. Okay, so the integral now, to set it up, the total area is going to be then the integral. In this example, we're running 1 to 4. 1 to 4, 2 pi x squared, square root of 1 plus 4x squared dx. Right? And just like in my previous example, I mentioned how arc length integrals and the surface area integrals, they tend to be pretty tough integrals. This one I'm sure can be done maybe by trig sub, or maybe another method, probably a trig sub, but these are typically done numerically. I like to do these numerically because The numerical methods, they pretty much always work. So I go back here if you're wondering about how to do the integral review. I've got videos on how to work these numerically in Microsoft Excel. They can be done in just minutes. And the nice thing is that method works for pretty well all of them. You don't have to know a half a dozen different integration techniques. So the purpose of this video is how to set up an integral for a surface area for a element revolved about an axis. I hope that this has accomplished that for you. Have a great day.